Hello everyone, I'm Yang Peng from Nanjing University. Today I'm going to talk about the lithospheric thermal structure and rheology in southeast China. The nature of the rheology of the continental lithosphere is a long-lasting topic in solid geophysics, but is controversial. More importantly, it still remains an outstanding question that how the rheology influences the continental tectonics. It is well known that both variations in temperature and rheology of the lithosphere directly influence the long-term tectonic stability, interplate or intraplate deformation, and the distributions of strains and stresses. The lithospheric thermoreological structure has been introduced to explain the plate-forming process, basin inversion, lithospheric folding, supercontinental cycles, the structure of orogenic belts, and rift and craton edge evolution. The researchers have done some works on China continent. They found a high temperature low strength in Tibetan plateau and a low temperature high strength in cratons like Western Sino-Korean craton and Yangtze craton, and the coastal region in the east shows a medium temperature and strength. The southeast China can be divided into three major tectonic units, which are Yangtze Craton, Caucasia Block, and the South China Sea. This region has experienced intensive Meso-Cenozoic intracontinental deformation. However, a regional high-resolution thermoreological structure of the lithosphere is still missing. Also, the relationship between thermoreological properties and regional tectonics is unclear. Therefore, here we wish to explore present thermoreological characteristics of the lithosphere in southeast China and their implications for regional tectonics. Here, the thermal model is constructed with the consideration of steady-state heat conduction. Two boundary conditions are set: the surface temperature and the surface heat flow. The mantle heat flow equals surface heat flow minus crustal heat flow. The two adiabatic lines are used to calculate the final thermal lithospheric thickness. Based on the compositional model and thermal model, we use the yield strength envelope to estimate the integrated lithospheric strength. The brittle and creep deformation can be described by Beerley's law and power law dislocation creep equation, respectively. According to Crust 1 model, we divide the lithosphere into 5 layers: the sedimentary layer, upper crust, middle crust, lower crust, and upper mantle. The heat flow data is taken from the International Heat Flow Commission database and the latest compilation of China continent. Here we show the thermal and rheological property parameters in the calculation. We assign the exponential decay model for the heat production and the temperature-dependent conductivity model to the upper crust, while in the other layers we assume a constant value. We define the crustal rheology according to the seismic velocity and then assign different rock types and corresponding rheological parameters to each layer. The detailed values are shown in the tables. Now we analyze the results. We will start with the thermal structure of the lithosphere and then move on to the rheological structure. Here we show the mantle heat flow and the thermal thickness distribution in southeast China. We can see the lithosphere is thick, more than 160 kilometers, and mantle heat flow is low in northwestern Yangtze Craton. Also, the lithospheric thickness decreases and mantle heat flow increases from the craton interior to the coastal zone in the southeast. Here, we present the deep temperature distribution in different depths. We can see the remarkable contrasts in different tectonic units. In 20 km deep, the temperature in Yangtze Craton and the Causation Block is similar, and slowly higher in South China Sea. However, in 40 km, the temperature is lower than 600 degrees in Yangtze Craton, but higher than 800 degrees in northern South China Sea. This contrast is more remarkable in 60 km and 80 km deep. We further use other geological and geophysical data to constrain the deep temperature. Here, we show the position of the Cenozoic xenoliths found in southeastern China, which are almost located in the coastal region. The lithospheric thickness indicated by the xenoliths thermal barometers is 60 to 100 km, consistent with our estimations in this region. In addition, the xenolith pressure temperature points from the mantle fall within the two calculated geotherms of the South China Sea and the Causation Block with heat flow data, indicating that our thermal model agrees well with the xenolith thermal barometers. The uppermost mantle seismic Peng wave velocity is another indicator of Moho temperature. Here, the black lines are the temperature range calculated from the Peng velocity. As can be seen, the temperatures at Moho predicted by the heat conduction equation fall well within the ranges determined by the Peng data. Therefore, the thermal model of the lithosphere in southeast China given by heat flow here is robust and constrained well by other independent both geological and geophysical proxies. Now, we discuss the results for the rheological structure. Here, we give the streams distribution of the total lithosphere, the crust, the mantle, and the percentage of crustal strains to the total strains. We can see that the middle and northwestern Yangtze Craton has the highest strains. The fraction of the crustal strains is lower than 40% in these regions, indicating that most of the Yangtze Craton is of a strong mantle lithosphere, consistent with the jelly sandwich rheological model. While the strains in northern South China Sea and eastern Causation Block is relatively low, the crust retains more than 60% of the strains, indicating a strong crust but a weak upper mantle for the lithosphere there, supporting the creme brulee rheological model. We also give the yield strength envelopes of different tectonic provinces. The envelope positions are shown in the map. The blue negative values represent the extensional condition, and the red positive values represent the compressional condition. It can be seen that the lithospheric integrated streams in compression is larger than that in the extension. But the brittle ductile depth in compression is lower than that in the extension. The BDT depth is around 13 km in Yangtze Craton's core, while it decreases to 10 km in the Causation Block in compressional condition. In addition, the lithosphere in the ocean and continent represents a big difference. Here, we show the strength profile from the western Yangtze Craton to the northern South China Sea. We found that the lithospheric integrated strength has a positive relationship with the thermal thickness, but a negative relationship between the surface heat flow. The thickness of the mechanical storm layer in the upper mantle decreases from northwest to southeast and almost disappears in the northern South China Sea. Now, I'd like to give some discussions about the results. First, I will talk about the tectonic modifications that lead to the present thermoreological mosaic structure. In Mesozoic, the flat slab subduction of the Paleo-Pacific plate resulted in broad intracontinental deformation in South China. After 150 million years, with increase of slab dip angle from a very low angle to a median angle. The corresponding rollback of the slab induced the magmatism to migrate towards the coast. Accordingly, magmatism-associated thermal weakening is evident in the coastal area. In the western area, the geological evidence proves the existence of the Meishan mantle plume in the late Permian, and this process dramatically modified South China. In addition, large-scale Cenozoic geodynamic process could further enhance this rheologically mosaic pattern. The Indo-Asia continental collision drives mantle material to flow outward. However, obstructed by the rigid Yangtze craton, the flow shifts towards the south. This extrusion distracts the southwestern Yangtze craton, giving rise to the observed high temperature and low strength anomalies. We also discuss the control of the thermoreological structure on the Cenozoic intracontinental deformation. The numeric simulations show that the more temperature increases and the strength decreases during the rifting of the continental margin. This is consistent with the thermal weakening of the Mesozoic subduction dehydration and late magmatism. According to the prediction of the numeric model, the present more temperature and strength ratio pattern will lead to a wide rift. So, we propose that the inherited tectonic heat effect in southeast China controls the continental margin rift and the subsequent opening of the South China Sea. In addition, the lithospheric thermoreological structure controls the distribution of the intraplate earthquakes. In the temperature profile from continental interior to the ocean, we can find that the seismicity is limited within 600 degree isotherm. In the strength profile, we find the seismicity almost distributed in brittle mechanical strong layers in the upper crust. Besides, the seismicity aggregates in low strength and strength transition zones, like middle northern Yangtze craton. This kind of seismicity pattern has also been observed in other continents, like North America and Australia. We also draw the histograms of percentage of seismicity versus the integrated strength of the total lithosphere, crust, and mantle. We can find that more than 50% of the seismicity occurs in a relatively low strength. In summary, we report the present lithospheric thermoreological structure in southeast China. We found the remarkable heterogeneities of thermal structure and rheology of the lithosphere. The majority of the area is of high mantle heat flow and temperature thin lithosphere, except for the western Yangtze craton, where a cold and rigid mantle exists. We also found the relationship between multiple tectonic modifications, thermoreological pattern of the lithosphere, and Cenozoic intracontinental deformation. The flat slab subduction of the Paleo-Pacific Ocean and far-field effects of the Indo-Asia collision modulate the thermal region and rheology of the lithosphere in southeast China. The thermoreological pattern and tectonic inheritance control the continental rifting, the opening of the South China Sea, and the distribution of intraplate seismicity. That's all. Thank you for listening.